welcome to Polynomial Graph Characteristics. Let's get started. Alright, so let's go over what these graphs may look like. So I've got 6 different kinds and I'm going to show you a constant linear quadratic, which these three actually we've learned, cubic, quartic, and quintic. So an example of a constant graph would be something like y equals 2. Okay, so it has a degree of 0. So y equals 2 would just be a straight line on the positive 2. Has a degree of 0, just a straight line. A linear graph would have a degree of 1. Right, we know what a linear graph, something like y equals x or y equals 2x plus 1, something like that. So if I was doing y equals 2x plus 1, it would look something like this. But basically it's just a line, right? It has a degree of 1, just a line. Quadratics, we've learned it's got a degree of 2 because it's got x squared in it, right? So it has a degree of 2. So in this case, we know it's a parabola. So that's kind of the shape of that quadratic function. Now we're starting to move over to cubic. Cubic would be an example like x cubed. Okay, and it could have, plus 2x squared minus x, it could have anything after that. But the greatest degree is 3. So the graph could look something like this. Okay, a quartic, just like it sounds, is going to have x to the 4th, and it could have other stuff after it, just like the x squared, just like the x. And it has a degree of 4. Okay, and it can do something like this. Okay, that's kind of the shape of that quartic function. Quintic would be x to the 5th, and that would mean it has a degree of 5. So there's an example of a quintic graph here. So hopefully you notice that the degree kind of highlights how many times it's crossing that x-axis, right? 1, 2, 3, degree of 3. Degree of 4, 1, 2, 3, 4. Degree of 5, 1, 2, 3, 4, 5. Okay, so that's one thing I want you to notice from there. The other thing is all the odd degrees, so 1, 3, and 5, they go in opposite directions, right? So one side goes towards negative infinity, and the other side goes towards positive infinity. That's important to notice. Whereas the evens, right, 2 and 4, they both go the same way. So these both go to positive infinity, these both go to positive infinity. So that's another thing to pay attention to. So let's kind of write that out. So an odd degree polynomial, just like we said, those are the ones, and I'm drawing them here for you to see in the video, but you have them on your graphs, on your notes. So they're the ones where each end goes different ways. So what that means is our end behavior is different. So odd behaviors have different end behaviors. Right? One side is going towards positive infinity, whereas the other side would be going to negative infinity. Okay, so that's one thing to remember about odd degree polynomials. The other thing is, just based on looking at the graphs, you can see that the domain goes all the way to negative and positive infinity, and so does the range, because if one goes down and one goes up, then they must also be going from negative infinity to positive infinity. So for odd degree polynomials, domain and range are both negative infinity to positive infinity. Okay, so 2 things to remember about odd degree polynomials. Even degree, so those are the ones where they both go the same way. So that would be one thing. They have the same end behavior. So both sides, or both ends of the graph, go towards positive infinity or negative infinity. So they do the same thing. Now, their domain is also going to be negative infinity to positive infinity because these arrows go out all the way. We knew that about the quadratic. But the range, you'll have to read it, right? It's called bounded. It means you have to read the lowest point to the highest point. Okay, so for the even degree, only the domain is negative infinity to positive infinity, so not the range. All right, so let's look at another example of the graph. If I have a negative x squared, we know from quadratics that means it was reflected over the x-axis. So it's a quadratic that's facing down. Whereas that positive x squared is going up. Okay. Now let's look at a different graph, the negative x to the fifth. Well, this is not the exact graph at all. It's going to look something like this. Okay, whereas if we did the positive, so if it wasn't negative, instead it would go this way. Okay, so this is what I want you to notice. When our leading coefficient is negative, remember leading coefficient is the coefficient in front of the term with the largest exponent, with the degree. If it's negative and we have even, so this is even, the negative makes it reflect. We remember that from quadratics, where if it's positive, it's facing up. That goes for all even degree polynomials. But for the odd degree polynomials, it changes the way, it's still reflected, but it changes the in behavior. So if it's positive, it starts from negative infinity and ends up positive. But if it's negative, it starts positive and goes towards negative. So let's kind of talk about that here. If your leading coefficient is positive, I'm just kind of summing it up, and it's an even degree, then both end behaviors are going towards positive infinity. If it's a leading coefficient, even degree, but it's negative, then both ends are going towards negative infinity. All right? Now, if we've got the leading coefficient is positive, but it's an odd degree, right, so remember that's x to the third, x to the fifth, whatever, then it's going to look a little bit still like the ones we just looked at. So it's going to come from negative infinity and go towards positive infinity, right? So that the right side will go towards positive infinity if the leading coefficient is positive. If it's an odd degree and it's negative, then it's the other way. It's going to start at positive infinity and go towards negative infinity. So the even degree is easy for me to remember. The odd degree is a little bit different. So I always remember if the leading coefficient is positive, then the right side will be going towards positive infinity. Whereas if the leading coefficient is negative, again, the right side will be going towards negative infinity. So if that helps, just somehow you need to remember the way that these graphs are going to go based on their leading coefficient. So just remember, if the leading coefficient is negative, it's something like negative x cubed or negative x to the fifth, something like that. Now I know that was a lot to take in. There's just one more little thing I wanted to tell you, and then we'll do some examples. But if you have a polynomial, so in this case we have a quartic, so it's crossing 4 times, right? But in this case it only crosses once, twice, and then here. So what you need to know is that when you have a root by itself, so we'll get to the factoring later and finding our roots, but in this case we'd have roots that cross here. Okay, so crosses at -4, we can see that. This line goes through -4. Crosses at 3, it goes through +3. But this one right here, because it's a double root, right? So if you solved, you had to separate them both, solve, you'd get x equals -1 and x equals -1. We call that a multiplicity of 2. Or you could say, in this case, it's a double root. So what happens when you have that double root? That's from here. Well, you get an x-intercept that bounces off, basically. So instead of going through, like these did, When it gets to the root at -1, it turns direction and goes back the other way. Okay, so we'll learn lots more about this later, but if you end up with a double root, right, multiplicity of 2, the same number, it bounces. So if you see a graph like this, then you need to be able to say this is one root, this is 2, because it bounces. So that would give me a total of 4 roots, which makes sense because we have a quartic function. So just make sure you write this down somewhere. We'll go over it more. But I will write here that I'm going to call it a bouncing root. It's not the official term, but a bouncing root means you have, it means 2 roots, so like a double root. It's just the same number. All right, so here we are with some examples. So just by looking at the graph, we need to be able to answer these questions. Okay, so the degree, I've got 1 root that goes through, 2 roots, 3 roots, 4 roots. They all go completely through. There's no bouncing. So this must be a 4th degree polynomial. Okay, now my leading coefficient, I know that my degree, because it's 4th degree, it's even. I can also tell that because both ends go down, so they have the same end behavior. But because they both face towards negative infinity, my leading coefficient must be negative. My domain for any polynomial will always be negative infinity to infinity. But because it's not an odd function, you'll see that my range, I have to read it. So in this case, it would be negative infinity to whatever my highest point was. So I'll just say 4.5. Now my end behavior, we've done this many times, but it's been a while. So I would say as x approaches negative infinity, so that means on this side of my graph, right, as my x-axis is going towards negative infinity, where is my graph heading to? What's it doing on the y value? Well, y approaches negative infinity. Same thing here. As x approaches positive infinity, my graph's going towards negative infinity. Right? We said even degree polynomials. This is even. Actually, all you really need to be able to say is this is even, not even 4th degree. But because it's even, we know that the end behavior must be the same, right? So they should both be going towards negative infinity. So one more example, just by looking at this graph, because one's going towards negative and one's going to positive. Their ends are going different ways. I should know that this is odd. Okay. If I want to count the roots, one goes through, this one bounces, so that would be 1 root. This would be a double root, so it actually would be 3rd degree. But at the very least, you should be able to tell me it's odd right away. The leading coefficient, because it's odd, I look at the right side. This is going towards positive infinity, so it must be a positive leading coefficient. The domain of any polynomial is negative infinity to infinity. Because it's an odd degree, one's going towards negative, one's going towards positive, that's also my range. And the end behavior, as x approaches negative infinity, and as x approaches positive infinity, we know with odd degree polynomials, they're going to have different end behavior. So the negative infinity, which is the left side, is going towards negative infinity. And as it's going towards positive infinity, which is the right side, it's going towards positive infinity. Okay, and this is just a reminder from before that you can still evaluate a polynomial at any point. We would evaluate linear functions and quadratics, and you can still do that with polynomials. So if I have this polynomial and I want to find g of 1, right, here was an x, now it's a 1, so I need to go plug in 1 for any of these x's. That still works here. It just takes a little longer. 1 cubed is 1. 1 squared is what I would do first, which is just 1 times 2, minus 1 minus 4. So I'd have 3 minus 5, which is negative 2. So what that means is that when my x is 1, my y is 2. Negative 2. So I should be able to find that point on this graph. So yeah, when my x is 1, my y is negative 2. So there's that point. Okay, that was a lot of information. I know the graphs are confusing, the odd and even degrees, the end behavior, bouncing roots, and then remembering and evaluating. So please rewatch the video as needed. Okay, all throughout the quarter you can rewatch it as much as you need to understand. The videos are not meant to watch once and just understand it. You have to go back sometimes, many times. All right, that's it for now. Thanks for watching.